We now define fundamental group of the space. So first you fix the space X, and then you fix a small point small x in this capital X space. So we denote this fundamental group by this pi1 capital X comma small x. So this is defined to be set of homotopy classes relative to boundary of the unit interval 0 1 of loops in the space X, but based at this point X. And you have the product operation of the two homotopic loops. You first travel U, then you travel V. So this is homotopy class of these loops U. So I'm just going to draw a bunch of loops here. One loop, two loop, and then another loop in green. Now this is well defined. Now suppose you have this space with a hole in it. So then you can have two loops which are not homotopic to each other. So one loop goes like this and another loop goes around the hole. And then in that case these two loops are not homotopic. Now the above is well defined, since if U is homotopic to U prime and V is homotopic to V prime, then we can paste these paths together. To get first travel U and then travel V is homotopic to first travel U prime and then travel V prime. So now a theorem. This pi1 capital X comma this point in the space X is a group. So the identity is the constant path, and the inverse of the path or the loop is given as U bar, and we have already shown this. So this is what we have done till now. Now we have to show that this pi1 is a functor. So what does pi1 do? It takes a space with the base point. Suppose this is a space with the base point. It takes it to a group. So this is the functor we have. So say you start with two spaces x and y. X and y are based spaces. So x has the base point x and we will say y has the base point y. And you have a continuous map f between them, which maps base point of space x to base point of space y. Now first thing is, since f is continuous, it takes loops in x to loops in y. So there are loops based in point x. You apply f to it. It will take base point to y, and the loop u would be carried to f of u. Now since f is continuous, it also respects homotopy. So say there are two homotopic loops in space x. So both of these loops, say u and v, are based at point x. And u is homotopic to v. So map f will carry a base point to y and these homotopic loops to homotopic loops. So f of v and f of u are homotopic to each other. So this just follows from the continuity of f. So this map f This therefore induces, since it carries loops to loops and homotopies to homotopies, this induces a group homomorphism from fundamental group of space X to fundamental group of space Y. So this F subscript star is a group homomorphism. So obviously we are talking about based spaces here. You have assigned particular points in the space. So it takes a homotopy element U to F composed with U and multiplication of two elements, say U and V. So first travel U and then travel V. This will go to first travel F composed with U and then travel F composed with V. So if you are given homotopy in space X, you just take that homotopy and just compose it with F. You get the homotopy in space Y. So notice that first you travel U and then you travel V. This is equal to this product which we have given in the definition. Finally, to show that pi1 is a functor, it should able to go from X to Y to Z. So let me be precise what I mean. So say you can go from space X to space Y by preserving base points using map F. And then you apply map G, which again preserves the base point, that is carries small y to small z via map G. Both F and G are continuous. Now this will induce the following maps on the loops. Yeah, you have in space X, you have a loop based at X, you apply F to it, you get to Y, and then you have F of U, then you apply G to it, you get Z, but now you have G of F of U. So G of F of U. So let us now write down the corresponding maps in the fundamental groups. So you have pi1 of X comma X. So you have the first homomorphism. So pi1 to be a functor, we have to show that if you first apply F star and then G star, this is same as the homomorphism of you first apply F, then apply G and take the homomorphism. So that is, this diagram should commute. So we should be able to get the commutativity in this group diagram, and that will imply that pi1 is a functor. Now to show that, first notice that G of F of U, this thing is equal to, you could directly go from space X to space Z. So first apply F and then you apply G. You could go directly from space X to space Z. So let me draw this in yellow. You could do this. Via this map. And this will immediately imply that you can, the second part, the one which I've written in yellow, so that will give you map G of F star, and this is equal to the first map. You first apply F star and then you apply G star, which is equal to G of F of U. And that is it. You can also write now for a map for ID on X. So instead of F, you just write ID on X, and then that ID on X also induces an ID map on the fundamental groups. So those are the three conditions which will show that this is a functor.